Alright, now that we've talked about inequalities a little bit, we can talk about the domain of radical functions and rational functions. So when we talk about domains, we can list them as inequalities, we can list them in interval notation, we can list them in set builder notation. When we're specifically talking about radical functions, that means that there is a radical. In this case, we're talking about square roots. We want to think about everything that x can't be. So we're not going to list all the values that it can be. We're going to list what it can't be and then write our notation from that. So looking at this first example here, it says k of x, so the function k of x equals the square root of 1 minus x. And I want to think about, well, when I'm doing square roots, the only thing I can't take a square root of is a negative number. So everything under that radical, when I simplify it, has to end up 0 or positive. So if I wanted to write that as an inequality, I could rewrite that as 1 minus x needs to be positive or 0, so it needs to be greater than or equal to 0. Right? So anything greater than 0 is positive, or it could equal 0. And then I solve that inequality for x. So I subtract 1 from both sides. I have a negative x greater than or equal to negative 1. I have to divide by negative 1, which means x is less than or equal to positive 1. If you think about that on a number line, if you're a visual person, all the values less than 1 would be here, going down, less than, shade left, and it could include 1. So if I wanted to write the domain of this in interval notation, the answer would be starting at negative infinity up to 1 and including 1 in my solution. So that's everything that x can be, right? Because I set this restriction at the beginning saying that that value, I thought about what it couldn't be. It couldn't be negative. Everything under that radical, once simplified, has to end up positive. So it can't be negative, so I set it greater than or equal to 0. That greater than keeps this side positive or equal to 0. I solved the inequality, graphed it to see the answer, the solution set, and so now my domain is all the numbers negative infinity up to 1. If you're ever unsure if you found the correct domain, you can test some values, right? If I put in, say, negative 2, you're worried that, well, negative 2 is a negative number. That doesn't make sense. How can I put in negative 2? Because I thought that this had to be positive. Well, it's saying once it's simplified, it needs to be positive. So plugging in negative 2, I can see 1 minus, I'm plugging in negative 2, equals, that subtracting a negative becomes plus. So it does end up positive and it ends up a real number. Versus if I tried to put in something bigger than 1, so over here on my number line, like my mind might think, because I think it needs to be positive, if I tried to plug in, let's just say 2, oops, x equals 2, plug it into my function, 1 minus 2, well, 1 minus 2 is a negative 1, and I can't take the square root of a negative number. So again, it's about everything under the radical, once you simplify it, has to end up positive and not negative. That's why negative 2 was in the domain, but positive 2 wasn't. Let's look at this next example. Down here, again, we're looking at a radical function, and I cannot take the square root of a negative number. So this 7 here actually has nothing to do with my domain as far as what I can't put in. It's only the values under the radical. So all of this has to end up positive. And then I can take the square root and add 7. So this is really what affects the domain. That 2x minus 3 has to be greater than or equal to 0. It has to be some positive number or equal to 0. So I solve that by adding 3. 2x is greater than or equal to 3. Divide by 2. And x is greater than or equal to 3/2. Again, if I wanted to graph it, I could. Greater than, I shade up. Equal to, I include it. And so now I have my interval notation starting at 3/2, including it with that bracket, up forever to infinity. And there's my domain. Go ahead and try the 2 on the right. Alright, it says find the domain of each function. Function c of x equals the square root of 4x plus 5 minus 3. So again, this minus 3 does not change my domain. What changes the domain is what's under the radical. This quantity here, this expression, has to end up positive or equal to 0. So I set 4x plus 5 has to be greater than or equal to 0 to keep it positive or equal to 0. I subtract 5 from both sides. I end up with 4x greater than or equal to negative 5. Divide by 4. I'm dividing by a positive 4, not a negative 4, so the direction stays the same. And I have x greater than or equal to negative 5/4. In interval notation, that would be starting at negative 5/4 and getting greater, so going up to the positive infinity direction. You could also graph it if that helps you. And looking at this last one here, again, everything under the radical has to end up positive or equal to 0. So I set it greater than or equal to 0. I get rid of the constant by subtracting it from both sides. I don't forget my negative 5, greater than or equal to negative 30. I divide both sides by negative 5. And did you remember to flip the direction of your inequality? We divided by negative 5, so that direction flips to a less than or equal to, and a negative divided by negative ends up positive. So now it's less than, it's all the values going down to the left on a number line. They're getting smaller, so I would start with negative infinity and go up to 6 and include 6 in my interval notation. Alright, let's go ahead and try the rational. Now the rational functions are different because it's all about the denominator. So I cannot divide by 0, right? The denominator can't be 0. So there's no other restrictions. I can input any other number I want for x that I want. I just cannot have that denominator end up being 0. So when I go to find the domain of a rational function, I set 1 minus x, in this example here on the left. It can't be 0. It can be anything else, but it can't be 0. So if I wanted to subtract 1 from both sides, I'd end up with negative x. It can't be negative 1. Divide by a negative 1. So x can't be positive 1 because that negative divided by negative. Which makes sense. I could just look at this and say 1 minus 1 would give me 0. So x can't be 1. So if you're asked the only value that x can't be, it'd be this. If I wanted to write it in set builder notation, I would say, so this is the set builder, the set of x's such that x is real and x is not equal to 1. I've also seen it just abbreviated with just this piece here. So all the x's such that x is not 1. It's assumed to be real. In interval notation, it's a little bit more complicated. But it's everything except for 1. So it starts at negative infinity, goes up to 1, but doesn't include it. Union from 1 to infinity. So it's starting over again. I don't believe your homework has you write it this way, but I just thought I'd mention it in case you see it in the future. Alright, looking at part B here, we have the function g, and it's x squared plus 1 divided by x plus 6. Now there is an x in the numerator, but that doesn't matter. I can put any number I want into that x and it doesn't stop me. The thing I have to think about is the denominator again. So x plus 6 cannot equal 0. Well, what's the only value for x that would make that 0? X cannot be negative 6. So that's the only value that x can't be, because negative 6 plus 6 would give me 0. Again, if you were asked to write it in set builder notation, you would just say all the x's such that x is not equal to negative 6. And again, you might see it with the x is real and x is not equal to negative 6, but I've also seen it this way on your homework. Try the 2 on the right. Alright, looking at function h here on the right, we want to determine the domain of this function, which means we have to find the only value that x can't be. So this domain cannot equal 0. The only value that x can't be, x cannot be negative 3, right? So if I subtracted 3 from both sides, that would give me x is not equal to negative 3. And I can check it. Negative 3 plus 3, in fact, would give me 0, which I can't have. So we want the set of x's such that x is not equal to negative 3. That's the only value it can't be. Looking at example B, function r, it doesn't matter that there's an x plus 4 in the numerator. The denominator can't be 0 because we can't divide by 0. So the only value that x can't be is positive 8, because 8 minus 8 would give me 0. So all the x's such that x is not equal to 8. And again, we're assuming x is a real number.